let's begin. So we have the Tilio Feingold Otamu's paper, Statistical Foundations of Common Knowledge.
Great. Well, thank you very much for coming. As I was saying, everybody should feel free to interrupt me anytime. In fact, if you want to ask a question, don't use the raise hand button because I'm typically not good at multitasking and I'm not going to be able to see that. So just speak out. Okay, so we all know that common knowledge is very important for strategic behavior. The question here is, when and how does common knowledge obtain? When do agents get to common knowledge? Okay. And to answer this question, we look at statistics, right? So how do people get to know things, right? So they know things either because these things are theorems, they're facts, or they learn them from experience, from observations, right? So something like that should also hold for common knowledge. And that's the kind of foundation that we're seeking here. So we have a setting where agents have access to a large data set of observations that are informative about a payoff relevant parameter. And when I say agents here, they're not really agents because there's no one is going to take actions. Okay, so it's just going to be a multi-agent passive learning setting. People are just sitting there observing stuff and making inference about the payoff relevant parameter. The idea is that, you know, after this inference stage, they're going to play some kind of a game, but we don't look at that. So there's a complete separation between you know, action stage, which we don't model, and this sort of passive learning stage that we look carefully at. So they get a lot of data about this payoff relevant parameter, and we want to know when is it that common knowledge is going to be the long run outcome of Bayesian updating. So everybody's Bayesian here. Okay. So so we call that common learning. Okay, so when common knowledge becomes the long run outcome of Bayesian updating. Of course, the one agent case is well understood. That's just Bayesian statistics. And if you open up a good mathematical statistics book, you're going to find lots of theorems about when is it that posterior distributions converge to you know, point mass on the truth parameter. And there are classic theorems by Schwartz from the 60s and slightly more general result by Ibrahimov and Haslinsky. The multi-agent case is not nearly as well understood. So of course, if each agent is individually learning the parameter, that's going to imply common learning in two polar cases, when the agent's private signals are either perfectly correlated, in which case beliefs are going to be public, or in the other polar case, when the agent's private signals are conditionally independent, that is conditional on the true parameter, on each possible value of the parameter, the signals of the agents are independent, right? In that case, my signal is very informative about the parameter, but it brings me no information whatsoever about the private signals of the other agents. And I know that the other agent is observing all these sort of IID signals, and I know he's learning, and so you know, so there's going to be common learning. The problem, of course, is the correlated case. And Cripps, Ely, Maleff, and Samuelson have shown, so they posed this question of common learning. They were the ones who actually coined the term common learning and addressed this question for the first time. And they show two things. One is that in general, individual learning does not imply common learning. Okay, so they have an example with a countable state of signals where individual learning obtains, but common learning does not obtain. And they have a positive result when signal spaces are finite. In that case, individual learning implies common learning. And of course, that's true irrespective of the correlation structure. Okay. The issue here is that signals are private. And this privacy leads to an infinite regress of beliefs problem. Okay. So common learning requires that not only agent I learns the parameter, but he needs to learn that the other agent has learned the parameter and learned that the other agent has learned that the other agent has learned the parameter, and so on and so forth. So it's clear that it's not the infinitude of their counterexample that drives the failure of common learning. It's actually rather easy to construct examples of infinite signal structures, for example, with Gaussian signals, under which common learning obtains. So our question is, what is this important property of finite signals that more generally implies common learning? Okay, and also, when do infinite signals fail? So we want to extend Cripps, Ely, Mailofin-Samuelson result to allow for more general signal structures. We don't believe that saying finite or versus infinite, that's the right, and we know that's not the sort of the real reason why common learning obtains or fails. So let me show you the model. So we do everything with two agents. It's easily generalizable for more agents. Have a finite set of parameters. There's a common prior, P, little p. And it's the space of signals, private signals, that's going to be, that we're going to allow to be rather general. So there is a standard Borel measurable space of private signals. Okay, and you have the statistical experiments. So given a parameter theta, we have a joint distribution on the private signals. Okay, and that's the where period by period where the signals are going to be drawn from. So we're going to denote by pi I the marginal distribution of agent I's private signal. And we're going to have this absolute continuity assumption that if you look at signals of the fixed agent I, and you look at the effect of changing the parameter, that change is going to be absolutely continuous. And this is the notation we have for the log likelihood ratio. And we have an integrability assumption of the log likelihood ratio. That is the expectation of the log likelihood ratio is finite. And that's called the relative entropy. Okay, so a little notation. The relevant space of uncertainty here is going to be the space of the cross product of the parameter space and the space of infinite sequences of profiles of signal realizations. And that, of course, has a natural sigma algebra, which is the product sigma algebra. And there's an a priori probability on this space of outcomes, right? So let's start with p theta. So p theta is going to be basically, point mass distribution on the parameter theta, and then, IID draws from, from the experiments pi theta, okay? And at this ex ante stage, basically you get a mixture of the p thetas, weighted by the prior little p on theta. So that's our notation. So I'm going to denote by xit the private signal observed by agent I at time t, okay, which you can view as a random variable on the outcome space, okay. And to simplify notation, whenever I write, the set theta, I really mean, the set theta viewed as a cylindrical event on this sequence space. So we're interested in conditions under which the parameter becomes approximate common knowledge in the long run. So we need to be precise about what we mean by this approximation. So we're going to follow Maunder and Summit and measure proximity to common knowledge by means of the notion of common belief. Common p belief for p close to 1 is the strategically relevant notion of approximate common knowledge. This is what Maunder and Summit show. So we say that an event E is Q believed, it's mutual Q believed if every agent, given the okay, so there's a T here. It should have been a little clearer. So the event that E is mutual Q believe at time t is the event that every agent assigns probability at least Q to this event E, given that private private history of signals. Okay, and then I can iterate this mutual Q belief operator and get a notion of K order mutual Q belief, right? Which basically says that at time t, all agents Q believe E. They also Q believe that everyone Q believes E, and so on and so forth, K times. And if we iterate this to infinity, we get common Q believe, right? So that's the event that E, is Q believed by everybody, everybody Q believes that everybody Q believes E, and so on and so forth, infinitely many times. So this, so we can interpret Q as a measure of how close to common knowledge we are. So what's common learning? So we're going to say that agents commonly learn the parameter in probability if for any possible value of the parameter and for every Q, the probability that there's common Q belief of the true parameter approaches 1 as t goes to infinity. And there is a counterpart of that definition for sort of almost short convergence, where you say that under the true parameter, the probability that the true parameter's common Q belief at every time after t approaches 1 when t goes to infinity. And of course, if you replace in this definitions here common belief by mutual belief, you have basically individual learning, right? So individual learning means that each player is attaching probability at least Q to the true state, and that event, the probability of that event approaches 1 under the true state as time goes to infinity. And here you have the analogous definition for almost sure convergence. So as far as individual learning goes, there's no big difference between convergence in probability and almost sure convergence. And in fact, these are all equivalent to an identifiability condition on the marginal distributions over signals. Okay, so individual learning obtains if and only if you look at the marginals of agent I's signals, they identify the parameter. Okay, so whenever, you know, the distribution under theta and the distribution under theta prime coincide, so this implies that the two values of the parameter must be the same. So what's the problem? The problem is this infinity regress problem, right? So let's assume that each agent's marginal distribution identifies the parameter. Then, of course, with probability 1 minus epsilon under the true parameter, we're going to have that each agent is going to 1 minus epsilon believes the parameter. And let's say that this is going to happen after period tau 1. And then each agent is going to 1 minus epsilon believe that the other agent 1 minus epsilon believes the parameter. And this is going to happen, let's say, after period tau 2. And, you know, and then for every n, each agent is going to epsilon learn that the other agent has epsilon learn that blah, 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 that he learns the parameter, right, n times. And this is going to happen after period tau n. Okay. The problem is that it may very well be that this sequence of tau n's converges to infinity, so that common learning may fail. You always get that if you fix, you know, finite level in the hierarchy, and you look at, you know, just mutual learning up to that level of the hierarchy, then you get this sort of mutual learning. But you want everybody's sort of beliefs about beliefs and so on and so forth to converge sort of uniformly on the levels of the hierarchy as time goes to infinity, because that's what's required for common learning. So what's the insight of Cripps, Illy, Maleth, and Samuelson? So in the finite signal case, we know a lot about the tails of the agent's hierarchies of beliefs. And when I talk about hierarchies of beliefs, I'm talking about, hey, let's not even think about the learning case. Let's suppose that you already learned the parameter, okay, which is going to happen anyway. The issue here is, what do you think that the other guys have learned, right? So what are your beliefs about the private signals of the other agents, right? So we know a lot in this finite signal case about the iterated expectations, and in particular the iterated expected beliefs in situations like that. There's a nice paper by Dov Samet that shows that if you have a finite type space, then iterated expectations of random variables converge to the prior expectation. Okay, so at least these sort of expected higher order beliefs are sort of under control as you go up the levels of the hierarchies. Okay, of course, expected, you know, higher order beliefs is not the same thing as the beliefs themselves, right? So higher order beliefs are beliefs about beliefs about beliefs and so on and so forth, right? So Samet's result is about the expectations of these things, the barycentres of these beliefs, okay? And so that's very well behaved, okay? And what Cripps, Illy, Maleth, and Samuelson do is they also prove a concentration inequality, showing that the actual realized higher order beliefs are uniformly close to these expectations, which by Samet's result is already close to the prior. So you have a lot of control about what's going on in the high levels of the hierarchies of beliefs. Okay, and I already argued few slides ago that, for finite levels of the hierarchies, everything is also under control, right? And so they get control over the tails, and you already have mutual learning as far as any fixed level of the hierarchy. So that's their insight. So they level they exploit the finiteness of the signal space to get that kind of control over the tails of the hierarchies. So the first challenge for us is that in our setting, convergence of iterated expectations to the unconditional signal distributions is not automatically granted. Okay, in the finite signal case, you can always decompose the the signal spaces into finitely many subsets. You have basically, beliefs about beliefs and so on and so forth form a Markov chain, and finite Markov chains have this standard decomposition into into sets that are that are invariant and are restricted to which the transitions, the Markov chain, is going to be irreducible. Okay, and we don't have that kind of stuff in our world. So the first thing we do is we need to restrict attention to this case. Okay, so we need to work with assumptions on our signal spaces that under which this induced Markov chain of beliefs about the signals of the others have this sort of mixing property. Okay, so for us, this is going to be an assumption. Okay, and we know lots of sort of general conditions under which you get that kind of assumption. So we're going to have two variations of this property. Okay, when iterated expected beliefs converge to the prior uniformly in the agent signals, and when they only converge pointwise. And that's why we're going to have two main results in the paper for each of these two assumptions. Okay, so let me show you the theorems. I have about 7 minutes, so I want to jump to the sort of the setting that the assumption. So I need to introduce this auxiliary Markov chain that we talked about. So this is this is an auxiliary Markov chain related to the agent's iterated expected beliefs about their private signals. And this chain, as I mentioned before, shows up in the theory of belief spaces, in Summit, for example, and it shows up in recent work by Golub and Morris on network games. And the chain is the following. So I have so everything is happening now in one period. Forget about time here. Okay, the time parameter in this auxiliary chain is actually levels of the hierarchy, not calendar time. So I have the joint distribution over signals, and let's fix the state at the parameter, which the players are going to learn anyway. So let's assume that they've already learned it. Okay, and they're formulating beliefs about the private signals of the others based on their observations of the private signal. Okay, so I'm going to denote by pi I theta the conditional probability of given I signal, the conditional probability of the signal of the other player. Okay, so pi I theta given a realization of I signal xi is the belief of agent I about the signal observed by the other agent when he observes xi and knows the parameter theta. Okay, of course, he won't know the parameter theta, but he's going to get pretty close to knowing it. Okay, so that's our auxiliary Markov chain. Oh no, we haven't gotten to the Markov chain yet. Sorry, we only know how to go from one player's signal to the other. Okay, so what we're going to do is we're going to go back and forth. Okay, so I can go from one agent signal to the other and then go back. Okay, so that I'm going to iterate these conditional probabilities. Okay, so pi theta, times p not I theta, okay, is agent I's expectation of agent not I's belief about the private signal of agent I when I's signal is x and the parameter is mutually known to be theta. So now I have a Markov chain on the signal space of agent I. And I also have a Markov chain on the signal space of agent not I. I'm going to assume that each of these two Markov chains is mixing. So mixing means that the n-step transition is actually going to converge to the invariant distribution, which is the marginal on agent I's signal. Okay, and I have a rate of convergence here, which is geometric, and I have this constant here, which may depend on x. And I call this function here the mixing function. So geometric, I have about 3 minutes, so I want to get to my theorem. So geometric mixing is not particularly strong. For example, in the counterexample of Cripps, Ely, Maynard, and Samuelson, geometric mixing does obtain. Okay, it's not the problem. Okay, I'm going to be able to present only one of our theorems, and that is going to rely on a slightly stronger assumption, which is uniform mixing. Okay. So I have two theorems, but let me focus only on this case. So I call the bounded case. That's when log likelihood ratios are all bounded, and where those mixing rates are also bounded. And in that case, I don't need any topological assumptions. When mixing functions are bounded, geometric mixing with those bounded mixing functions turns out to be equivalent to uniform mixing. Uniform mixing means that the n-step transitions approach the marginal distributions in total variation or uniformly in the state space, in the signal space. And the theorem is that if the log likelihood ratio functions are bounded and the signal structure satisfies this uniform mixing condition, then individual learning implies common learning. And of course, there are assumptions on primitives that ensure uniform mixing. And here's one set of assumptions. Let's assume that signal spaces are compact. Let's assume that the joint distribution over signals is absolutely continuous with respect to the product of the marginals. And this density here, f theta, is continuous and strictly positive. Then that's going to imply uniform mixing, and therefore, in that case, by our theorem, individual learning implies common learning. So I'm not going to be able to get to the unbounded case. So let me just wrap up. So when does common learning obtain? That's the question we ask. And looking at Cripps, Ely, Maynard, Samuelson, you may suspect that the answer to this question is compactness in one form or another. And while this is partially true, we show that the deeper reason lies in these notions of mixing, and another notion that I didn't have time to get to, which is relevant for the unbounded case, which is this property called common typeness. And this is it. Thank you.
Thank you. Now we have any questions?
Hi, is it possible to ask in Portuguese or is necessary to ask in English?
It's okay to ask. Pode falar em português. Eu acho que não tem ninguém que não fala português na sala, me parece.
It's more easy to think in Portuguese. Yes. Bom dia, tudo bem, professor?
Bom dia.
No seu principal resultado, que é o teorema, né? A questão da razão da razão de chance ser limitada é pelo fato de você ter definido ela como uma forma de entropia. Essa é a primeira pergunta, quer dizer, você de alguma forma, na sua intuição, você falou de entropia lá no início, mas né, não voltou nesse assunto novamente, mas no seu teorema você fala que a razão de chance lá, né, ela está de alguma forma limitada, né, que é uma das suas principais hipóteses. É justamente pelo fato de você ter definido ela como uma integral de entropia, né, quer dizer, você tem os agentes, cada um tem seus espaços de parâmetro desconhecido e ajuste da chegada de informação, e os dois estão tentando chegar no mesmo ponto, né?
Deixa eu
e aí é como se
esclarecer.
fosse dinâmico isso, é como se você estivesse tentando chegar num sistema dinâmico estável, quer dizer, você está tentando de alguma maneira você assumiu que está minimizando uma entropia entre esses pontos, entre pontos diferentes chegando no mesmo ponto. Eu fiquei com essa dúvida.
Não. O espaço de parâmetros é comum a todos, tá? É que eles estão observando sinais privadamente, tá? Então, você está sentado no seu quarto observando sinais privados informativos sobre esse parâmetro.
Legal.
E eu também, tá? E aí, mas eu não estou fazendo inferência só sobre esse parâmetro, eu também estou fazendo inferência sobre a sua inferência em relação ao parâmetro. E o meu sinal, ele é informativo, potencialmente, não só sobre o parâmetro, mas também sobre a sua inferência sobre o parâmetro, tá? Então, é essa situação multiagente, onde eu estou fazendo inferência sobre parâmetros, sobre a sua inferência sobre parâmetros, sobre a sua inferência, sobre a minha inferência sobre parâmetro, tá? E a questão da entropia realmente não apareceu de novo, porque a gente não chegou no segundo teorema. No primeiro teorema, eu assumo que as log likelihoods são limitadas mesmo, tá? E para o segundo teorema, não, eu permito que elas sejam ilimitadas, né? Como no caso gaussiano, por exemplo. O caso gaussiano é ilimitado, mas ainda é integrável. Então, eu preciso da integrabilidade e preciso de outras coisas também que eu não consegui abordar, tá?
Tá. E a segunda pergunta seria o fato de você ter usado lá só para entender melhor, né? O kernel que você diz, quer dizer, a intuição que veio lá do artigo lá de 2008, eu não consigo compreender muito bem, é como se você agora, você tratasse como se, como todo mundo tem capacidade de chegar sozinho, né, no ponto, né? Você passa a tratar a probabilidade, aquela expressão que você fez, né? Quer dizer, agora você está buscando uma forma de medir apenas a maneira como você está tratando o outro, é isso? Quer dizer...
Exatamente.
Que é o casinho, né?
De uma certa forma, as coisas são decompostas exatamente como você falou. A parte de aprendizado individual sobre o parâmetro funciona bem, né? E agora tem toda a parte complicada, essa inferência sobre inferência. Então, vamos imaginar que essa parte também seja relativamente sob controle, pelo menos em esperança, que é fixando o parâmetro, né, essa cadeia de Markov que me diz, né, dado o meu sinal, qual é o meu belief, qual é a probabilidade que eu atribuo ao teu sinal, né, e qual é a esperança que eu atribuo a sua posteriori sobre o meu sinal, né? Isso forma uma cadeia de Markov, né? Se essa cadeia de Markov, no caso finito, cadeias de Markov são super bem comportadas, porque se não for irredutível, ela vai ser, pelo menos a gente pode decompor em pedaços no espaço de estado, que é o espaço de sinais, que são irredutíveis e tratar separadamente aí o que está acontecendo nessas regiões diferentes, né? No caso geral, não existe essa possibilidade. Então, eu preciso, para começar, eu preciso de hipóteses que garantam esse tipo de comportamento estável, né? Mas isso não é suficiente, tá? Ainda preciso ter esse controle de concentração em torno dessas esperanças que estão todas bem comportadas. Tá?
Não, é muito impressionante. Valeu, obrigado aí. Muito legal. Obrigado.
Alright,
eu estou roubando o tempo dos outros.
We have to start with the next presentation.
Okay, so I think I'm next. Okay, let me see if I can share the screen. So, okay, I will stop Eduardo from sharing his screen. Okay, so thank you everyone for, I guess I'll be looking sideways. So let me see, okay, I'll not try to fix this now. So thanks for being here. So this is a joint work with Bruno Bassanetti, who's now at our sister institution in Rio, EPGE. So signaling in dynamic markets with adverse selection. So I think I'll be done in 20, 25 minutes. Let's see if I can make on my promise. When you think of markets in which there is adverse selection, okay, so this is a substantial change of topic relative to the previous talk. So when you think of markets in which you have adverse selection, I guess it's fairly natural to think that that you should have, or you would have, signaling through prices. Now, so if you think of, let's say, over-the-counter markets for financial products, okay, so this will happen whenever the informed party, okay, makes an offer, sort of offers a price. Okay, so if you want to buy this from me, you have to pay a price P. Okay. So this seems like a sort of a very sort of a non-controversial assumption, or not controversial assumption, but a non-controversial statement. Okay. Now, despite this, most of the literature on dynamic trading with adverse selection, okay, focuses on screening models, meaning models in which it's the uninformed party that makes offers to the informed parties. Okay. But we know since the seminal work of Wilson in 1980 that the price setting mechanism affects market outcomes. And so I guess sort of a very natural question to ask is, okay, so what happens in a dynamic decentralized market in which you have adverse selection? Okay, what happens when you have signaling through prices? Okay, and this is what we do in this paper. Okay, so we study signaling through prices in dynamic decentralized markets with adverse selection. Okay. Now, so a common intuition that you have sort of across, there are lots and lots of papers. Not lots and lots, but there are many papers written on dynamic trading in the presence of adverse selection, okay, whether it's in centralized markets or decentralized markets. Okay. And so a common intuition is if adverse selection is severe enough to prevent agents from agents to pull, meaning from trade to take place at a single price, okay, then you're going to have a delay in trade, okay. Now, so trade is not going to happen instantaneously. This, of course, amounts to an efficiency loss. Okay? And the standard intuition that you have is that, well, if you think of a seller that has a higher quality good, okay, so these sellers, they have a greater opportunity cost of trading now because the good is more valuable, okay, for them, okay, and so they're willing to wait longer to trade, okay. And so delaying trade restores trade by ensuring that the owners of these the lower quality goods do not want to pull themselves with the owners of higher quality goods. Okay, and so what happens in screening models of trade is that by lowering the opportunity cost of trading, meaning that sort of making this delay in trade less costly for agents, this is going to reduce the ability of buyers to screen sellers. And this is going to lead to a loss in market efficiency. Okay, so you make the market less frictional, and this actually leads to a worsening of the trading outcomes, because essentially what you're doing is you're reducing the ability of buyers to screen, let's say, the sellers of lower quality goods. Okay, so our paper does more than that, but this is the result that I want to emphasize here is that in a setting in which instead of having screening, you have signaling through prices, okay, this intuition breaks down completely, okay? So in a sense, what we show in this paper is that market efficiency is actually going to be independent of trading frictions, okay? So this is sort of the main result in the paper, okay? Now, I'm not going to discuss the related literature. I think anyway, it's a 30-minute talk, so I guess I'm excused for not doing that. So let me jump straight to the environment, okay, and walk you through some of the results that we have in the paper, okay. So we think of a timing where you have discrete time and infinite horizon, okay. There's a single indivisible good, okay, which can be of finitely many types, okay. So we'll use calligraphic I to denote the set of possible types of the good, and for things to be interesting, I need to have at least 2 types of the good, okay. In each period, you have a mass 1 of anonymous infinitely lived agents and an equal mass of anonymous. I have a mass 1 of infinitely lived sellers and an equal mass of anonymous infinitely lived buyers who enter the market. Okay, so the sellers can produce 1 unit of the good and are privately informed about its type. And I have this fraction Fi, positive fraction of type I sellers in the population. Okay. So in each period, you have this mass 1 of sellers entering, a fraction Fi of them is of type I, and I have a mass 1 of buyers entering the market as well. Okay. Now payoffs are very simple, okay, so we have this quasi-linear structure, okay. So if I'm a buyer, I buy a type I good at price P, my payoff is Vi minus P. So Vi is the value that I attribute to the good. And if I am a seller and sell the good at price P, and I'm a type I seller and sell the good at price P, my payoff is P minus Ci. Okay. And so Ci is also non-negative, and this measures the opportunity cost of trading for me. Okay. So we assume here that Vi and Ci are non-negative and strictly increasing in I. Okay, so there's a sense in which goods of higher type are of higher quality, meaning that buyers have a higher valuation, and at the same time, sellers have a greater opportunity cost of parting with them. Now, when we depart from the literature in not assuming that our framework is flexible enough that we can allow for the difference Vi minus Ci, which is a measure of gains from trade. We do not need to assume, as is fairly standard in this literature, that this difference is increasing in I. Okay, so we don't need to have, and in fact, we may even have negative gains from trade for some types of the good. Okay? But I'm not really going to have time to discuss, sort of much chance to emphasize this in the presentation. Okay, now, so trade takes place as follows. In each period, buyers and sellers in the market are matched in pairs. Sellers, they post a price, which the buyer either accepts or rejects. Okay, if the buyer accepts, they trade and exit the market. Okay, otherwise a match is dissolved and these agents remain in the market. Okay, so we assume that as soon as you enter the market, you get the chance to trade. It doesn't really matter if you have to wait 1 period before being able to do that. Okay. So trading frictions. Agents have a common discount factor delta. Okay, and the idea is that reduction in delta reduces the opportunity cost of not trading. Okay. Now we get similar results if delta is an exit probability, okay, or if buyers and sellers in the market are matched with the probability alpha between 0 and 1 in each period, okay. So nothing changes, okay, qualitatively, okay. So how do we describe behavior, strategies, and beliefs? Here, I'm going to use, it's simpler to work with what we call distribution of strategies, okay. So instead of talking about individual behavior, I'm going to talk about aggregate behavior, okay? So a strategy profile for the sellers is a list of probability measures on R+, so sellers post no negative prices, such that mu I of P is the mass of type I sellers who post a price in the set P, okay? And a strategy profile for buyers is going to be described by this map from R plus into 0, 1, saying, well, what's the probability that if I, as a seller, offer a price P, what's the probability that this price is accepted? Okay. Now, an equivalent way of describing the strategy profile for buyers is using not this instantaneous probability of trade, but a discounted probability of trade, which is given by theta of P, which is sigma of P over 1 minus delta times 1 minus sigma of P. Okay. And I have to talk about beliefs. If I'm a buyer and I meet a seller that posts a price P or asks a price P to trade, I need to form a belief about what is the type of seller that I'm dealing with. Okay. So pi I of P is going to be the probability that I attribute to the seller being of type I if the seller asks a price P to trade with me. Okay. So now I can sort of, and here I'm just going.
Sorry, can I ask you a question?
Sure.
So are you assuming some kind of, are you restricting attention to some stationary strategies or something like that?
So that's the slide I'm on. Okay.
So
I'm describing beliefs and I'm not putting equations. Okay, because anyway, the equilibrium definition. Sorry, I'm describing equilibrium. The equilibrium definition is fairly standard. So I have a notion of seller optimality, that seller's price posting behavior is optimal given the buyer's acceptance behavior and their payoff from not trading. Okay. A buyer's optimality, meaning the buyer's acceptance behavior is optimal given their beliefs and their payoff from not trading. So I have what we call rational beliefs, meaning that beliefs satisfy Bayes' rule for prices on the path of play. So these are the prices that are offered in equilibrium by sellers. So I need payoff consistency in the sense that the payoffs, okay, which are used, they are consistent with the behavior of agents. And I need stationarity. That was Eduardo's question, okay? So I want the inflow of each type of seller to equal the outflow, okay? So these are the conditions sort of that define an equilibrium, okay? So a few remarks are in order because agents are anonymous, okay? So buyers have to get the same payoff in equilibrium, or we'll call it V. And each type of seller, the type I sellers also need to get the same payoff in equilibrium, or we'll call this EOI. Okay? And the stationarity assumption, okay, there's a typo in there, it implies that all goods must trade in equilibrium. Okay. Now, one thing that we depart from the literature, okay, and this is anyway something that we like to emphasize, is that we do not impose any equilibrium refinement in our equilibrium. Okay, so and the idea here is that we want to be agnostic about the belief formation process for prices that are off the equilibrium path. Okay, so in a sense, we're asking, okay, what can we say about the equilibrium set with essentially just imposing Bayes' rule and stationarity. Okay, now what happens? Okay, because it's a question that we get often. Okay, what happens when you impose standard equilibrium refinements? Okay. And if we impose intuitive criterion, the answer is that it doesn't refine the equilibrium set at all, okay? And if we impose the other standard equilibrium refinement, which is D1, it reduces the set of equilibrium to separate in equilibria. And as you're going to see, this is not going to change substantively the nature of our results, okay? So now let me define welfare, okay? So if you give me a strategy profile, I can compute what is the probability that a type I good trades in a given period, okay? And it's this expectation here at the top of the slide, okay? Now what I can think is for each type of seller, imagine that a type I seller enters the market, and in a sense I want to compute what is this discounted probability of trade, essentially the expected number of periods it takes for the seller to trade, okay? So this is given by this ratio here, okay? And what I do is for each seller, I look at the discounted probability of each type of good. I look at the discounted probability of trade for the type I good. I multiply it by the gains from trade for that type of good, VI minus CI, and I multiply this by the fraction of type I goods in the population, I sum, and that's my measure of welfare, okay? Now, that's a warning. I'm not going to really have time to elaborate on this. So it's sometimes people actually define welfare in this environment, not by this way that we defined, but by average payoffs in the population, okay? Now, it turns out that in this environment, these things need not be the same, okay? And this can happen when sellers randomize, okay? So we have to work with this definition of welfare here, okay? So let me describe quickly the basic properties of equilibrium, okay? So the first one is that seller payoffs restricted decreasing in seller types, okay? And this is a standard result in this literature, and because essentially the intuition is very straightforward, because lower type sellers have a lower opportunity cost of not trading, they can extract a greater information or rents from buyers. It means that the payoffs are going to be greater, okay? So seller payoffs are going to be strictly decreasing in seller types, okay? Now, because of our stationarity assumption, this together with stationarity assumption implies that it's possibly only the highest type of sellers that can make offers that are rejected in equilibrium with probability 1. All other types of sellers, they make offers that are accepted with positive probability in equilibrium. The second property, and this is something that follows a rather straightforward consequence of incentive compatibility, is that if I look at a price that a type I seller posts in equilibrium and a price that a higher type, a type J seller posts in equilibrium, it has to be that in equilibrium, the higher type of seller always posts a price P prime that is not smaller than the price that a lower type of seller posts. Okay, so I have this monotonicity property of prices. Okay, and also, okay, and this is because I'm going to use this later on, is that if you look at discounted probability of trade for a price P, it has to be, and this is a consequence of this, anyway, this implies it's monotonicity, but I want to emphasize that, is that the state of P has to be non-increasing, okay? So I increase the price, the discounted probability of trade at a price cannot increase. And if I look at the prices that are offered on the path of play, this actually has to be strictly decreasing when I restrict attention to the set of prices that are offered in equilibrium. Okay. Now, so a consequence of this property number 2 is that the set of prices at which trade takes place in equilibrium is finite. Okay, so let me skip intuition for this. Okay. And finally, okay, the result that I want to emphasize is that if the average quality of the good, the value of the good to buyers in the population is smaller than the cost of the highest seller of parting away with this good, okay, that's a situation that we call severe adverse selection. This implies that the equilibrium has to be pulling. Okay, again, the pulling outcome is not an equilibrium outcome. Okay. So now let me go to the essentially sort of the main result in the paper, okay, is that the set of equilibrium payoff vectors for equilibrium which the payoff of buyers is 0, the set is invariant to the discount factor delta, okay. So this is, and yeah, I'm just going to give you sort of I'm not going to be able to walk you through the proof, okay. So what happens when buyers payoffs are 0? When buyers payoffs are 0, prices have to be equal to the expected quality of the good. Now fix a discount factor and a probability of trade. Okay, so I can look at this on the term on the left hand side. This is the discounted probability of trade when the instantaneous probability of trade is mu. Now imagine I have a different discount factor delta prime. I can always change the instantaneous probability of trade to a new value mu prime such that the new discounted probability of trade is equal to the original discounted probability of trade. So this means that if I keep prices the same and I can adjust seller behavior when I go from discount factor delta to discount factor delta prime, if I keep prices the same, I can adjust the seller behavior so that I keep the discounted probabilities of trade the same. And thus seller payoffs the same. Now, what's the challenge here? Okay, the challenge is that by adjusting seller behavior, I'm changing the equilibrium masses of sellers that are in the market at each point in time. And so I'm changing buyer beliefs. I'm changing how buyers update beliefs conditional on receiving a certain price offer. So the main, and essentially the result here consists in showing that we can adjust seller behavior in such a way that we keep both the discounted probabilities of trade and the buyer beliefs the same. Okay. So anyway, this is, you have to take, I don't know, have to believe my word, sort of what I'm saying, but this is the content of this proposition here. Now let's sort of briefly talk about separating equilibrium. So because anyway, these are equilibria that are they capture in an intuitive way the idea that price is signal quality. And our main result, the trading frictions are dependent of market frictions, is going to be rather straightforward when you have separating equilibrium. So let me denote by SI the set of prices that type I sellers offer in equilibrium. So in a separating equilibrium, if I look at any type less than the highest type, so this type can only offer a single price, and this price has to be accepted with positive probability. This is a consequence of results that I stated before. Now, the highest type of seller, they can offer more than one price. Okay, if some of these prices are rejected in equilibrium, this is not interesting for what we want to say. So our claim is that V is equal to 0 in any separating equilibrium. Okay, let me walk you quickly through this claim. Okay, so if I look at buyer optimality, okay, so if I receive I as a buyer see a seller posting a price P1, I know that I'm dealing with a type 1 seller. Okay. There's a typo here. So if I trade the price P1, my payoff is V1 minus P1. And this payoff has to be greater than my continuation payoff from not trading. So I'm only going to be willing to trade if the price P1 is sufficiently small. It has to be less or equal than this W1, which is the difference between V1, the buyer, the value of the good, type 1 goods to me, and delta V1, okay, my discounted continuation payoff from not trading. Now, what happens when this price is smaller than W1? Okay, now me as if I'm a type 1 seller, one thing that I can do is I can deviate and offer a price that is between P and W1. Now, at worst, so the worst possible case, okay, so if I look at the expected value, I am as a buyer, I see a price that is between P1 and W1. I know that in the worst possible case, this is a type 1 seller that I'm dealing with. So my expected valuation is at least V1. So if I look at the buyer's payoff from having the price P prime between P1 and W1, okay, this is at least V1 minus P prime. Now, because P prime is less than W1, this difference V1 minus P prime is greater than delta V. So I, as a buyer, I'm very happy to accept this price. And in fact, I'm willing to accept it with probability 1. Now, because of that, then a type 1 seller can actually profitably deviate, increase slightly. If P1 is less than W1, I can slightly increase the probability of trading. Okay. I can trade at a higher price with probability 1, and of course that P1 less than W1 cannot be an equilibrium price. So it has to be that P1 is equal to W1. But if P1 is equal to W1, this is only possible if buyer payoffs are equal to 0. Okay. Now, okay, so I can land on the sort of the two main slides. Okay, so a straightforward consequence of this result, because remember, let me go back to the result that the set of equilibrium payoff vectors in equilibrium with V is equal to 0 is invariant to delta. And in this case, welfare is determined completely by the discounted probabilities of trade and consequently by the seller payoffs. Okay. Now, because I showed that in a separating equilibrium, V is equal to 0, then an immediate consequence of this result is that the set of possible values of equilibrium welfare for separating equilibrium is invariant to the discount factor. Okay. Now, what's the problem with dealing with separating equilibrium is that when I have at least 3 types, there exists non-separating equilibria that Pareto dominate and lead to higher welfare than any separating equilibrium, even when adverse selection is severe. And intuition, very quick intuition, is that induced separation can be very costly, especially if the lower type of seller is in a small proportion relative to the other types of sellers. Okay, so focusing on non-separating equilibria, you might be missing on some equilibria that have, I don't know, much better efficiency properties. Okay, so the question is whether our result extends to when you actually to non-separating equilibria. And how have our main proposition, okay, which is maximum equilibrium welfare is invariant to delta. Okay. And there are a number of steps in the result. The first step consists in showing the welfare when V is equal to 0. Welfare when V is positive is bounded above, welfare when V is equal to 0 is bounded above by average seller payoffs in the population. And it's actually equal when sellers do not randomize. Okay, so that's the first step in the proof. The second step in the proof is to show that in any equilibrium, for any equilibrium with V positive, I can find a more efficient equilibrium when V is equal to 0. And finally, the third step is that for any equilibrium with V is equal to 0, I can find a more efficient equilibrium which sellers do not randomize. These three steps together, they lead to the result that, well, you maximize well for an equilibrium with V is equal to 0, and sellers do not randomize. But then you go to our main claim, okay, that the set of equilibrium pair vectors for these sellers is invariant to the discount factor. Consequently, the maximum equilibrium welfare is going to be invariant to the discount factor, okay? And with this, okay, with no conclusion, because anyway, the conclusion is the result that is in the slide, I finish, okay? I know, so maybe we should skip questions and go straight to, but anyway, so if someone wants to ask a quiz question, I'm happy to take it. Or we can, I don't know, leave questions for after Rafael's presentation.
We should allow a little bit of time for questions. All right, then I think I should start my presentation. So thank you very much for accepting my paper. This is rather different from the previous two papers that have been presented here, because this is a paper for greater interest to, I think, macroeconomists. And the only thing the papers here share in common is that they are papers without any data in them. In this case, what I'm doing is that this is a project that I started recently, so it's very preliminary. And it is about how an economy adjusts when you change the physical environment of the economy. So traditionally, you think about the study of comparative statics, where you look at like an economy in general equilibrium. You have your economy in general equilibrium. It has like preferences, endowments, technologies. And this physical environment induces into a allocation and prices. In this, and then we think about how a shock to this economy, a change in the environment, changes the allocation and prices. You can think about trade models, where you model countries as general equilibrium models, and you change the parameters and then you change the equilibrium. What I'm doing here is that, okay, so a topic that might be interesting is that the adjustment of an economy might be subject to frictions, in the sense that there should be a process in which prices and allocations adjust to changes in the underlying environment. And this process might last some time because of frictions. And then I developed a model of endogenous adjustment frictions that provide some kind of micro foundations for the common assumptions you see in many macro models that involve convex cause of firms changing their capital stock, for example. So I consider a general equilibrium environment where information is assumed to be sticky. The stickiness here means that it takes time for the information regarding existing trade opportunities to diffuse through the agents in the economy. Like the way I model here is that I model this stickiness by assuming that the agents have constrained consideration sets. So you take a consumer in the economy, the consumer doesn't have instantaneous access to all firms in the economy. The consumer can only trade with a subset of firms, and this subset of firms is subject to rules, and these consideration sets, they evolve over time, and this evolution over time that creates these adjustment frictions. So this paper is very different from other papers that I know, and perhaps the simplest, the closest one to this paper in terms of philosophy would be the Menkel-Reyes macro paper about how agents adjust to changes in monetary policy, where they use a sticky information model that only a fraction of the agents know the real money supply, and this fraction grows over time, and this yields then, this implies that the money supply is not, the economy is not neutral to money. So changes in money supply creates real changes in output because of this sticky information regarding money supply. here I'm extending this concept to stick information regarding the opportunities to trade with the other agents in the economy. So since this model is very preliminary, what I'm thinking about is developing this theoretical framework in different directions. And among these different directions, then it can result in different papers. So this is basically a research project that I'm just beginning. So one application is that it can explain why you can have price-taking behavior even when you have substantial frictions of trading markets, in the sense that the market would behave as if it is perfectly competitive, even though it shouldn't be perfectly competitive. It can also explain, this is the main result here, that why an economy adjusts slowly to shocks in the environment, so why prices and allocations will take a while to adjust to changes in the underlying environment. And it also can result in that the equilibrium allocation in the economy can change over time, even though there is no changes in the environment. So you can have equilibrium where the environment is fixed, but the economy changes without any changes in the resources, endowments, preferences, and technology. So I assume that time is discrete. I consider a environment with a representative household. The representative household consumes a basket of L final goods. The representative household has a utility function in each period. And this representative household is inhabited by a continuum of consumers, workers, and entrepreneurs inside the household. Right, I'll measure one. So what are these consumers, these workers, and these entrepreneurs? So each entrepreneur runs a business in some sector L. And this business employs workers and produces goods. So you can think this is a firm. The idea is that these firms, they can change sectors over time, and there will be frictions in which these firms operate that I will go into detail soon. So the first friction you have is that the entrepreneur has a constrained consideration set. So the entrepreneur can only set a business in a subset of the economy, of the sectors in the economy. So produce L goods. There is only one factor of production in this model, so there is only labor, and there is no complexities in production. You just have labor in one side and the L goods in the other, and each firm produces one of the L goods depending on the sector the firm is. But you as an entrepreneur, then you can choose in which sector to operate, but your choice is constrained by your consideration set, and your consideration set depends on the time. So your entrepreneur J has a consideration set that is a subset of the sectors where he can set up a firm. So then at the beginning of period T, you choose the sector in ATJ to run a business that is the most profitable. The profitability then includes the prospective future profits, right? But I will skip over most of the notation in the model in this presentation because of time constraint and because the model has a lot of notation because it has a lot of moving parts. So the consideration set of entrepreneur is determined as follows. So you consider an entrepreneur who's operating at sector H in period T minus 1. So we are interested to know in which sectors this entrepreneur can operate in period T. So in period T, you can continue operating sector H if you want to, if you find it profitable to do so. But you can also have access to another sector L with some probability, right? So because we have a continuum of entrepreneurs, then it means that a fraction of the entrepreneurs in sector H in period T minus 1, this fraction psi T L will have access to move their business to sector L. And then this probability then is assumed to be a function of certain parameters, certain variables in the economy that are equilibrium variables actually, which is that the profitability of sector L relative to the economy-wide average. So the idea is that the more profitable sector L is, the higher is the probability that entrepreneurs in other sectors of the economy will pay attention to sector L and will have the possibility to move to sector L. It also is an increasing function of the total population of entrepreneurs in sector L, which is just the fraction of the measure one entrepreneurs that are in sector L. The idea is that, okay, so a sector that is very profitable and is very large could be a sector that lots of entrepreneurs will be aware of and will be able to move there if they think it is profitable to do so. Sectors that have lower profitability than the economy-wide average will not tend to be in the consideration sets of entrepreneurs in the other sectors of the economy. The key friction here is that this probability is not one, even though the profitability might be higher than the economy-wide average. If these probabilities were equal to one, essentially the entrepreneurs will have access to all sectors in the economy, and there will be no frictions in this sense. An entrepreneur then is characterized by the type, which is the sector they operate in, the age of the business they are in the industry. So the idea here is that the age is a very important parameter for the entrepreneur, because it determines how long he has been operating in the sector, and this age determines then how many consumers and how many workers he can reach. So you have frictions in each sector and between consumers and workers and entrepreneurs. And there is also then the technology parameter, which is the production cost, is how many units of labor you need to consume to produce 1 unit of the good L. And the entrepreneurs, then they are the price makers, they are the market makers in the economy, they post prices to consumers and wages to workers. And then as well, consumers and workers have imperfect information regarding the entrepreneurs. So each consumer has a consideration set, ATL-I for consumer I, and the worker I, I'm using notation here, we have a consideration set ATI, right? So we just assume then that the consumer will shop at the cheapest entrepreneur in the economy that the consumer knows for good L. So the consumer wants to buy some good L, he will shop at the cheapest store selling good L among the stores he has access to. The worker I will then work for the best wage he can find among the entrepreneurs in his consideration set. So how these consideration sets for the consumers and workers are determined? So they are determined by the signal parameters of the entrepreneur. So what are these signal parameters? So any entrepreneur of age A will be feature a pair MA and NA of parameters to consumers and workers. These are two real numbers, and these real numbers, they represent the intensity of or the size of their potential base of customers. So if you are an entrepreneur with the signal MA, it means that you have this potential customer base MA of consumers, which is a population of consumers that are aware of you and incorporate you in their consideration set. And you have a potential labor force NA, which is a subset of workers that are aware of you and incorporate you in your consideration set. So from the point of view of workers and consumers, the number of entrepreneurs a consumer and a worker knows is distributed according to a Poisson distribution, which is with parameter MTL, which is the weighted average of these MAs. So the MTL is the weighted average of the MA theta for each type of entrepreneur theta, and then you have the set of entrepreneurs operating sector L, and you just sum over all these entrepreneurs and weighted by their population, delta T theta. So if you have a population of, suppose all entrepreneurs of the same type, and there is only one sector in the economy, so the measure one of entrepreneurs are in that sector, then workers and consumers will have on average MA of these entrepreneurs in their consideration sets distributed according to a Poisson. So some consumers will have 0 entrepreneurs in their consideration set. Some consumers will have 1, some have 2, but on average they'll have MA. And workers in the same way will have 0, 1, 2, 3, etc., with on average being NA. So what happens is that these parameters, they are assumed to evolve over time because they represent the diffusion of information regarding entrepreneurs in each sector, right? If you just take MA and NA to be equal to infinity, then you get perfect competition. So then this model becomes a standard general equilibrium model if you just assume these parameters to be equal to infinity, or you take them to infinity, the equilibrium will converge to perfect competition. But what we assume here is that these parameters are bounded and they are non-decreasing to represent the idea that information diffuses over time. So we start with these parameters, starting levels ns and ms and ns. And when you take a to infinity, they will converge to m hat and n hat. And then they are assumed to be like weakly greater than ms and ns, to represent the idea that the longer an entrepreneur is operating in a sector, more consumers and more workers will have access to that entrepreneur. It is that the firms that are older are more well known than the firms which are younger. So they compete by posting prices, and we can think about the way they compete in this form. So we have the entrepreneur J and the entrepreneur J prime here, and they are in the same sector, so they sell some good L. The entrepreneur J here has like a parameter M, and the entrepreneur J prime here has a parameter A, M the same size. And then this represents then the potential customer base of the entrepreneur J. And this potential customer base, if you suppose there are only two entrepreneurs in the model, we can think that they only compete against each other, and then they will have these captive customers here. They will have these customers here who are aware of both. They have access to both, and then they will have captive customers here. So this setup here is basically the same as in a standard Burdett-Judd model of price dispersion, where you have price dispersion because you can always extract some profit from your captive customers, but you also have the incentive to undercut the competitor to extract profits from these customers who are aware of both firms. But what happens here is also there is also the supply side of the market here. So you have this simultaneous interaction between the demand side here and the supply side here. So this interaction here means that sometimes the equilibrium might not feature price dispersion in one side of the market because entrepreneurs will be constrained by the supply side. And then the competition for workers operates in the same fashion. So you expect to get price dispersion for wages here. Okay, so then you as an entrepreneur, you maximize profit subject to the constraint that the quantity you sell to consumers is feasible given the output that you produce at some wage W. So you post the wage to your potential labor force, and this wage will yield then a supply of workers for you. If this wage is very low, then the workers receive poisson signals from the other firms. So if you post a wage that is very low, these workers will go to the other firms. If you post a wage that is very high, you can capture a larger fraction of your potential workforce. And then given this wage you post, you get then your supply, and then you post a price to your consumers, and you cannot post a price that is too low, because if you post a price that's too low, then the consumers will demand more output from you than you can supply to the consumer. So you have to balance demand and supply. Each entrepreneur essentially balances demand and supply for this economy. So they are the market makers of the economy. And then they have to balance this to maximize profits. And in equilibrium, what will happen is that you don't want to hire more workers than you sell the output. So you never post wages that imply a higher output than the demands implied by the price P, right? And workers and consumers, they will spend, the worker will supply 1 unit of labor as long as wages are higher than 0. So we assume the household doesn't have any disutility from supplying labor to the economy. So the worker will be happy to work for any wage higher than 0. So the equilibrium distribution of wages will have support starting from 0 to some upper bound wage, strictly positive wage level. The consumer then, they will spend some quantity determined by the household on good L. So this means that the consumer demand will have elasticity of 1, because the household will choose how much to spend on each consumption good, and they will send the consumers as their agents to the firms to purchase the consumption good. So then the firms will face demand curves that are isoelastic, that you have a fixed amount of money from the consumers that they choose to purchase, but you compete with the other entrepreneurs to satisfy this consumption demand. The household then will take then the prices implied by this interaction between consumers and firms. The interaction between consumers and firms will yield some prices, expected prices, and these expected prices are the prices the household will pay for the good, because the household has a continuum of consumers. And similarly, the household will have expected wages that the household will receive from its labor force, and the household also owns all the entrepreneurs. They are part of the household, so the income of the household is the aggregate between labor income of entrepreneurial profits, and the prices then are the expected prices that consumers transact from, and the household maximizes utility in each period, given this. So then the equilibrium concept here is Markov perfection, right? The idea that how agents maximize utility given their environment and given the state of the economy in the current period. So at each period, you have then a distribution of prices for good L, a distribution of wages, and this distribution will be profiles of distributions for each type of entrepreneur. And you have the choices of consumption by the household and the value functions of entrepreneurs. And this will yield then the distribution of entrepreneurs across sectors and the allocation of consumption goods for the economy and levels of employment for the economy. So the consumers purchase from the lowest priced firm in each period. The workers work for the highest wage given their consideration sets. The entrepreneurs operate in the most profitable sector in their consideration set. And given that they operate in that sector, they pose prices and wages that are in the support of distributions that are optimal for them. And the household then chooses the consumption to maximize utility. So the equilibrium has some interesting properties that I found out while working on them. And one interesting property is the idea that price dispersion might disappear under certain conditions. So you typically expect, because of the imperfect information consumers have regarding firms, that you have Burdett and Judd type of price dispersion in the markets for consumption goods, like as you can see in this picture here. Because of the existence of captive customers, you usually expect price dispersion in all sectors to occur. But because of the interaction between the supply and the demand side of the market, the market making firms or entrepreneurs running the firm, they will have they'll be supply constrained, and the supply constraint might imply that in equilibrium they will not be able to influence the market prices, even though they have captive customers, even though they have market power. They cannot exploit their market power because of the supply constraint. So this will happen if the degree of frictions in the labor market is higher than the degree of frictions in the industry L. So the idea here is that this is the Poisson parameter of the size of the consideration sets of the consumers and the workers. And if this Poisson parameter here is bigger than this here, it means that there is more intense competition in the demand side of the market than in the supply side of the market. Because the competition is more intense here, the distribution of prices will tend to collapse to a single point. As you basically you put them higher and higher, distribution of prices collapses to a single point. And at the end, when you have the equilibrium with the distribution of price at that single point, then everybody is acting as if competition was perfect, because your demand at that price becomes an interval that consumers are indifferent between going to one firm and the other, right? So if you look at the diagram here, the consumer here is indifferent between going to J or going to J prime. So if they pose the same price, so your demand then becomes the demand of these guys plus the variation in demand here. And then in equilibrium, you find the optimal to just choose a point inside the interval, in the interior of the interval. And so at the interior of the interval, your marginal revenue is equal to the price. So the market for good L will behave as if it is perfectly competitive. So this result, I'm thinking about just focusing on trying to implement this result in a more general environment and write a new paper about this. And then the other result is the idea that the economy will have frictions of adjustment because it takes time for these parameters M and N to grow. So if you consider economy two sectors, and the costs on each sector are the same, so C1 is equal to C2 for simplicity, and there is only one cost type of entrepreneur, so we don't go into detail about cost types in this presentation here, right? We assume then that there is no price dispersion product market, so that we can focus only on the competition for workers, and we have perfect competition in product markets. So the house has some lock preferences, right? There is a typo here. It's supposed to change over time. Here, the U is supposed to change over time, but you have your lock preferences. And then the function that determines the entrepreneur's consideration set can be written as this. So the measure of entrepreneurs that are aware of sector L, that do not operate in sector L, is 0.2 times the maximum of 0 in the case sector L is not very profitable. In the case the sector L is more profitable than average. So this is the profitability level of sector L minus 1, which means that if sector L is more profitable than the average, some entrepreneurs in sector H in the other sector will take notice of that and will consider moving into sector L. And then you have this parameter here, which is the population of entrepreneurs in sector L, right? And then the NS will start at 0.1 and you grow over time according to this. So in the limit, it will grow to 1. Okay, so this means then that you have information diffusion of workers regarding the entrepreneurs in the market. So suppose you take the economy in some stationary equilibrium period T with the preference of the household like this. So the household spends the same amount of money in good 1 and good 2. Suppose now there is a shock for the periods greater than T, a period T prime greater than T, the household receives a shock and its preferences change. So the household likes good 1 much more than good 2, right? And then you suppose the discount rate, which I didn't define earlier, but suppose the discount rate goes to the discount factor, sorry, goes to 1. So the entrepreneurs, they don't care about they don't discount profit, so they just go to the sector with the highest profitability rate in the steady state. So what happens? What happens is that then at period T, both sectors will employ the same number of workers at the same level of profitability. By period T plus 1, there will be a divergence in the relative profitability in each sector. And then given these parameters, then you have a movement of entrepreneurs from sector 2 to 1, right? And then there will be a change in the level of employment because of the frictions in the labor market. The idea is that because it takes a while for the workers to gain access to the firms operating, because the firms take a while to grow, then lots of firms shutting down in sector 2 and opening up sector 1 will result in an aggregate decrease in the demand for labor in the economy. Many workers will stop receiving offers from entrepreneurs in sector 1, and you take a while for information to diffuse. So this is sector 2 here, because the firms will move from sector 2 to 1. So this is a typo here. By period 19, the economy will attain a new stationary equilibrium, right? So then I just solved the model on Excel, this very simplified one. And then you have then the change in the workers' marginal product by industry, where taking the price of good 1 as the numerator or as the normalized to 1, you have then that the marginal product in industry 2 will fall dramatically because in the shock of preferences, and it will take a while to recover. And then the employment levels by industry will be the same initially, but then the industry 1 will jump and the industry 2 will fall, but the aggregate employment level will fall because of the frictions. So you can think that in the case of the COVID shock, you have like restaurants and you have delivery, food delivery and restaurants where you go to the restaurant. So if you have this COVID shock, then this will imply in a decrease in aggregate employment just because of these adjustment frictions in the economy without any frictions elsewhere. Okay, so I run out of time, it's already 10. So I will just skip over here and wrap up. So I just presented this model of adjustment of market allocations to exogenous shocks. And it means that this adjustment process takes time due to the existence of these frictions that they represent by constraint consideration sets. Supply side frictions imply that price taking behavior can occur in product markets, even though you have information frictions among consumers, right? And then that's it. Any questions?